Hello to everyone who's joined already. Just to let you know that we'll be starting shortly. We're just waiting for everyone to join, and we'll be starting at the top of the hour. Okay, I think we'll get started. It's just gone the 3 o'clock here on British time. So many thanks for joining us today. My name is Sarah Bebbington, and I'm a publisher for IOP Publishing. For today's webinar, we've been able to bring together guest editors and contributors to a focus issue that has recently been published in our open access journal, Machine Learning, Science and Technology. The focus collection on machine learning for large-scale facilities is available now under our collections page, and the link is on the screen at the moment. Then there are also 2 handouts available to everyone who's joined today, and you can download those, and that's got the link to the collection page as well as extra information on the journal if you wanted to have a look at that. So everyone listening today will be able to submit questions via their questions pane on the screen, and we'll try to get through as many of these as possible. I'd just like to hand over now to one of the guest editors and organisers for today. That's Dr. Keith Butler from the UK's Rutherford Appleton Laboratory. Keith, over to you.
Thank you very much, Sarah. So yeah, I'd also like to join Sarah in welcoming you all here today. I'd also like to thank IOP Publishing for all their help in putting together this webinar, and also putting together the focus edition that we have on machine learning for large-scale facilities. So this webinar and the special edition was kind of conceived a couple of years ago when there was a workshop on artificial intelligence for photon and neutron sources being held at the ILL. And it's great to have the opportunity to see how things have developed in the field since then. So in areas from data analysis, data collection, accelerator optimization, you can find contributions on all of those areas in the focus edition, and lots of different types of methods, everything from kind of good old-fashioned Bayesian methods up to the latest reinforcement learning approaches. So during the webinar, we'll first of all have an introduction and a background to kind of how that first workshop came about and what people were hoping to get at that time, and why people thought that machine learning was important for facilities, and that will be Professor Tony Hay. Then we'll have 3 invited talks from people from facilities across the world who'll tell us about the latest in how machine learning is being deployed and changing the way those facilities are being used. And then finally, towards the end, we'll have a panel discussion where we'll have a panel of experts who are also editors on the special edition, and they'll discuss how they see machine learning developing in the future at facilities. So in the interest of keeping ourselves a little bit ahead of time, maybe I will hand across to Tony to give us the first talk.
Yes. Thank you very much. I'd like to show my screen, and I hope something will happen. Great. Okay. Okay. So yes, how did this come about? Well, I was working at Microsoft in 2012 when there was a breakthrough in machine learning applied to images, and I was working then with the many of the US labs and national labs and people like Brookhaven, Argonne, Oak Ridge and Berkeley, and I saw that they were actually looking at applying machine learning methods to scientific data. So when I came back to Rutherford Lab, I wanted to see that we could do something on the site here, and so that's how I got involved. So let me just quickly then go through and give you a bit of background. So this is the deep learning revolution, which took place in hold it a moment, let me just get that out of the way. For some reason, okay. It was essentially a simple neural networks have been around for many years with one hidden layer, and deep learning introduced many hidden layers and had a dramatic impact. And in particular, there was a thing called the ImageNet Recognition Challenge, where you could actually train a network on images or use any machine learning method you liked, but neural networks trained on these images which have been labeled, and then you could use it to actually see what if you could identify things in the non-test set. And the classification error rate when it started was much worse than human error rates, which was around 5%. But as you see, very rapidly, and in 2012 there was a dramatic improvement, and that was using deep learning with AlexNet, and it had evaluated the learning using GPUs, and that just continued. And so in 2015 there was a Microsoft entry which had up to 150 layers, hidden layers between the input and output, and that gets down to it shows here it's certainly around human level recognition accuracy. So that was the big excitement, and this is a slide by Andrew Ng. It's a bit of a marketing slide because it doesn't have any coordinates, just axes, but it's intended to show that deep learning seems to get better with the more data and the more compute you use, where older learning algorithms essentially saturate. So that is why deep learning became very exciting, and these are some of the accomplishments in industry. This is looking at Facebook, Amazon, Microsoft, and Google, and others. And so near human level abilities for images, for speech, for handwriting, translation, and so on. And these are all commercial applications. But what I was interested in, and what the US DOE labs were interested in, was seeing what they can do with the sort of images we produce with these big machines like synchrotrons and neutron sources. So this was the perspective I had from the US. These are the Department of Energy's AI for Science. They curate data sets. They have the most powerful computers in the world for science, and they have teams doing maths and computer science research. And they have these user facilities, such as the photon sources at Argonne, at Berkeley, and at Brookhaven, of course. And they're able to put together teams to do an end-to-end science solution. So that it's really an exciting environment to actually explore the limits of machine learning applied to scientific data. And just to show 3 projects. This is one from Brookhaven. James Sethian was actually a speaker at our Grenoble meeting, and this is the camera project. So it wasn't only machine learning, but this certainly showed that machine learning had some really great advantages. This is David Womble's sort of taxonomy of AI use cases at Oak Ridge: image analytics and surrogates, inverse problems, control systems, using various types of algorithms. And this is what they were doing at Argonne. They had a rather unique DOE and National Cancer Institute partnership, and they were producing applications to drive solving cancer, and see if you could run these benchmarks on the very big computers you have in the DOE, where, for example, Summit has thousands of GPUs, and that's a major resource. So that's what was happening in the US, and the exascale computing project, which had started before then, recognized this and set up a new co-design center for exascale machine learning, and it was run by Frank Alexander at Brookhaven, a colleague of Kirsten, who's here today, and Stuart, and involved the other labs like Livermore and Los Alamos. So I put this slide in especially for Keith, because it's about perovskites, and he keeps telling me how important that is. But this is one example of machine learning that they were doing in the ExaLearn project. And then in the Department of Energy Office of Science, they set up in the Advanced Scientific Computing Directorate a program on basic research needs for scientific machine learning with foundational themes, capabilities. So they were doing a lot of activity, and my concern was I wasn't sure how much was happening in the UK or Europe. I certainly didn't see much activity at the Rutherford Appleton lab, and that's why I was excited by this. So in 2019, the three labs I mentioned, Berkeley, Oak Ridge and Argonne, organized the AI for Science town halls, and over 1,000 scientists participated, and you can read the report looking at opportunities for applying AI in all these different disciplines, and also how you can actually advance AI by applying machine learning with physical constraints, with laws of physics and symmetries and so on. And so this is the outcome in 2019. So this was the workshop we put together in Grenoble with ESRF and the ILL synchrotron and neutron source, with diamond light source, and with the AISSSRFSP neutron and muon source at Rutherford Lab. So how did that come about? I got an email in February in 2019 from Philip King in ISIS saying, we've spoken about the idea of a facilities AI workshop, and I'd spoken with Robert McGreevy. The idea came up at the board of ISIS with Mark Johnson, who's director of ILL. And so that I was told that by both ISIS and Diamond that I was the contact point, and I was the person who had to liaise with Mark and his colleagues in Grenoble. And that was fine. This is the program committee we put together, and you'll see some of the members here today. And I think Paolo's here, and I think that's the only other person on the committee at the moment. But Paolo can tell you his view of the committee, and these are the sponsorship organizations, ESRF and ILL, Diamond and ISIS, and the department I was involved in, which is as a scientific machine learning group, it's the Department of Scientific Computing. So that was how the workshop came about. This is the list of speakers, and the idea was to get a list of speakers both from the US, but also from Europe, and we have also a speaker today from China, which will actually mean that it was a rather broad-based program, and I was pleasantly surprised to see the level of activity also in Europe and as well as in the US. But these were the speakers. We had about 20, and many of those are represented in this volume. So this is a view of the meeting. There were people there, and it was a very pleasant meeting. We had an exciting time, lots of discussions, and in those days we could meet for a drink and some cheese. So it was very pre-pandemic and very, very entertaining in November 2019. So what comes of that? Well, there is the possibility of a true transformation by AI of scientific research. And one of the curious things that I was asked to do by the DOE was to chair a committee looking at the results of the town hall meetings to look and see what opportunities and challenges there were for setting up a major program at the Office of Science in the DOE. And there's a report that you can read, which came out in September 2020, and I was the chair of that. So what's the goal? Well, I think the goal is to do science more efficiently, better, and to see both the strengths and the limitations of machine learning methods using neural nets, and to see whether we can do better, how we can improve on those. They have a well-known brittleness, and the idea is that we can actually use these scientific things both to do science, but also to improve artificial intelligence methods. And I particularly like the quote that was cribbed by David Womble from a Microsoft report, and it is, AI won't replace the scientists, but scientists who use AI will replace those who don't. So I think that's enough for me to say that, and I'll hand back to Sarah to actually take us to the next speaker. Sarah?
Hi, yeah, I am just now switching to Tim Snow is up next.
That's right. Thank you.
Hi there. Cool. Can you all see my screen? I think you can, if I've got this right.
Yes.
Yes, we can.
Excellent.
Thanks, Tim.
Looks good.
Okay. So I've called my presentation "When, Where, and Why Machine Learning at Facilities," and part of that is because obviously you want to deploy machine learning at the most useful location, or where it is most useful itself, but also you need some justification, because otherwise it's quite trying to crack a nut with a sledgehammer all over the place just because it's the current in vogue thing. So what I'd like to do is quickly go through some information about facility automation as it stands at Diamond today, and this idea of analytically driven experiments, which is something that we've been kind of driving towards for some time, but I'll show you where we've currently got to there, with the idea of then moving on to artificial intelligence and machine learning being in that analytical loop. So today, what can you expect? We have got really good, especially with macromolecular crystallography, at sending out pucks that look like this with pins on. You can put crystals on. You can then ship these to us, and they will be put inside a container with many others, and a robotic arm will go in and fetch these pins one by one, mount them onto some beamline, scan them, and then return them again. And that's great. That allows you to do many different experiments all together. And we've also developed a web system to kind of integrate these things together. So you can go from having a packing label that is created for you so that you can send things to us. You can then watch your experiments unfold before your very eyes, and you can see when your samples are being scanned. And subsequently, you can look at your data online, or alternatively, if you're very lucky, possibly some of your fitted structures as well. And that is essentially a more or less fully automated workflow from A to B. But there's no particular intelligence in this. These parts here are fully automated. For the data analysis, we basically run through a lot of different potentials in order to find out what is going on. But if your sample is unscannable, you might get a message returned to you saying there's no data set, but there's nothing to kind of intercept that at the time and try and do something about it just yet. Well, not routinely. So thinking now about analytically driven experiments, for anyone who's been to Diamond or has seen our systems, we currently use a piece of software called GDA on many of our beamlines for running experiments. I've just included a kind of simple UI here. And the idea is that you can put text or other entries into panels, press buttons to initiate scans, or we also have a command line as well. Behind the scenes, what we have is a server client setup that is powering the beamline, and there is an active MQ messaging bus that is present with the GDA server for certain types of scans, and that produces messages that can be intercepted by other pieces of software. I've included 2 pieces of such software over here. So we've got a couple of our in-house packages. So we've got data analysis and kind of reduction software called Dawn, and another messaging bus system called Zocalo that the macromolecular crystallography community especially use for doing their data analysis. And the messages that we send out have things like what the status is, name of your scan, where it's stored, some information about the last frame that went out, what the previous state was, so that you can do kind of state checking, the size of your scan and where you are. And what this allows us to do in near real time is present our users with multiple layers of data. So I brought up a scan that we were running on a test sample here, and in grayscale at the back, what you're seeing is the number of scattered X-rays that hit our detector face, summed up for the entire detector face. So this scan is ongoing. So we see down here that there's a little black section here. This is part of this scan that has yet to be concluded. So this line is still being acquired. And then if we go back from where we have the last grayscale point, which is, as I say, sum of number of photons on detector, we have this little red arrow here and a slightly larger over here. And that's actually data that we've taken. So we've taken that detector frame, we've reduced it down, and we've done some manipulations to it. And we've then analyzed that data and returned it to the users so that they can see what is going on as that experiment is proceeding. Obviously, there is a certain amount of overhead in another piece of software starting up, reading the messages, returning the results. And because of that, although the scan is currently here, we see that the analyzed data has a bit of a lag associated with it over here. And each one of these time points is about half a second. So we're maybe 5–10 seconds behind where the scan is, but nevertheless, we are somewhere close to near real-time data analysis. We are looking at ways to reduce this feedback loop by optimization of the setup, but for this test, we were reasonably close to where the scan was. Many years ago, when I gave a presentation, I was told that the biggest way to make an impact is to always leave a nice big empty space. And so I have done so down here because it's not only our software that can hook up to this messaging bus, it is obviously available to anything that has authentication. And that's where Python comes in, or any programming language that you want to hook up to the messaging bus. And that neatly leads us on to the idea of putting artificial intelligence or machine learning into that analytical loop. For myself, I largely see machine learning at facilities falling into one of 2 very broad categories. So we can either be helping users do more automated analysis, so maybe a number of choices need to be made, or classifications, or there are seed parameters to go into fitting engines. And then there's the other kind of side of things whereby you want to run things more automatically, or you want to help people deduce endpoints and other things, or what the next scan point variable might be, and that all falls under the idea of intelligent scanning. So it might be that you want to do quick classifications or something to help with that, whereas for the automated analysis, maybe you want a slightly more in-depth routine. And sticking with Route 1 for a moment, that leads us to the paper that myself and the other authors on our publication, so that's Andrew, Joss, Tom, and myself, wrote for that special edition, where we were using Bayesian analysis on some X-ray reflectometry data. So this is where we're trying to determine parameters about thin films on an interface by reflecting X-rays off the surface, in order to work out the amount of informational density that they had for the different parameters that you can potentially fit. The reason we were interested in this is that a lot of people come along to an experiment and they say, all right, well, I know that I need to fit this parameter because that's what I'm most interested in, or I need to fit this parameter because that's kind of somehow tied to another parameter. So in our example, we have what's called lipids. These are molecules that are made up of a hydrophilic and hydrophobic part, so a part that likes water, likes to be in water, and a part of the molecule that doesn't like to be in water. And therefore, there is a reasonable assumption that because these things are tied atomistically, that you can't have, say, 2 of one to 1 of another if you have a 1-to-1 relationship in your molecule. So when fitting various parameters, you may envisage constraints initially, but what we were looking for here was a more automated, more data-driven way of trying to both highlight the amount of informational density in these parameters, but also which parameters from a statistical background make the most sense to fit. And something that we also found was, what one might already guess, it is possible to overfit your data as well. So if you fit every single parameter known to man, then yes, you can do this. Yes, it will potentially give you a very good fit, but the actual amount of information that you're extracting out starts to recede. Leading on from that, another article that was published by one of the authors, so this is Joss, but also who was at the time a placement student, graduate student, Daniil, James, Rebecca, also from the SciML group, and Joss, was this idea about rather than going from a kind of Bayesian approach to work out what information density you have, use machine learning networks. So in this case, we have neural networks to do that initial classification such that you can get out initial parameters that you could use for fitting. So I've taken a figure and a table and conflated them together for this here. And we can see that from their machine learning algorithm, they predicted some values. They then took these values and put them through a classical fitting engine, which in this case I believe was RefNX, and they fitted those values to get a slightly more refined potential answer. So both of these approaches are great ways towards automating data analysis. In the back of my mind, I still feel that it's quite useful to combine these two techniques actually. So in the paper, or this particular paper, you see that for up to a certain number of layers or a certain number of parameters, it's possible to create a machine learning network that allows you to parameterize, see all of these different variables and do a fit. But obviously, if you have an ill-posed problem, which machine learning is, which reflectivity is, and if you then put that in with an infinite number of parameters, it can be very difficult to see all of the different potential, all the different areas you could go down. Whereas if you do some pre-classification to start with to work out the kind of things that you might want to fit, that could help you classify which network it is that you may then want to use in order to look at that data. And seeing as one of the first things that was mentioned by Keith was want to see the kind of latest things in this area, I recently saw this paper also in the machine learning area in this journal. So I quickly put together a slide just getting a couple of figures out. And as you can see, this is another example of using a neural network, in this case with 1,000 neurons, in order to look at neutron reflectivity data. And it has the words accepted manuscript cast upon it because it's only just recently come out. So thinking back to what I was saying about different ways of deploying machine learning at facilities and building on the workshop that we had in Grenoble, one of the things that was highlighted by the camera group, so this is some of the work that Jamie Sethian was showing us, was this idea of how you could go from doing just a pure grid scan, so a scan with regularly spaced points, to doing a more adaptive scanning, so something that's looking at the data and trying to work out where informational density is, such that you scan fewer points in order to acquire the same kind of richness of data, which potentially can allow you to dramatically speed up your acquisition by reducing the amount of data that you need to acquire. It may be in the future, as we move towards more fly scanning or continuous scanning modes, that you may not see such increases in the speed of acquisition. So the continually moving row to row, going through an entire scan may be more performant than going to particular areas. However, as detectors get larger, beams get smaller, it may be that this becomes a more preferential method on the basis that it may only generate a fraction of the data, which both in terms of storage and then processing is also quite an enticing thought. So as a kind of general thought process going through my mind, I was thinking, okay, so at the moment, it is possible for us to analyze data and therefore kind of monitor deviations in a system. with respect to time. We can, in the system that we have that I showed with a messaging bus, not only receive information about a scan that's ongoing and do something to interpret that data, but as I kind of hinted to with the fact that we can return results into our data acquisition client, we can also trigger other scans as well. So at the moment, it is possible for us to do this kind of level of work, although it's not commonly used at the moment, although I feel that COVID will definitely be coming into play for that in the not too distant future. Inferences based on prior art, so this is looking at using machine learning either on examples of already existing data that's been published or simulated data to work out what next experimental parameter you might want to vary and by how much, is the kind of work at the moment that's very much ongoing and will, I feel, in the not too distant future be where we end up, and whether that's to inform the next step or to help people with their data analysis, 6 of one, half a dozen of another, but I feel that that's the next step. Finally, down here, I put dynamic triggering of synthesis. So maybe you're doing some chemical synthesis on a surface, or maybe you're doing something in solution, coupled with scanning, allowing potentially for automation of a whole visit. I put in red here because it seems a little bit far-fetched in a way, which got me thinking. So I thought we have all of this technology. So going just one step kind of further, obviously this requires quite a lot of work now, but there have been a lot of publications recently. It's kind of started, or I started hearing about it through the Cronin group up at University of Glasgow, this idea of taking raw ingredients and there being a machine learning closed loop optimization that's going through and trying to produce a particular outcome for you. But of course, a lot of this would happen in a lab rather than in a beamline. But then there's also been quite a lot of advances recently with robotics. So there's a company called Boston Dynamics that will now sell you this robot down here called Spot, which you can attach arms to. And this uses machine learning and other optical recognition packages in order to navigate its way around. And it could be the thing that takes the sample from the lab and carries it out the door, puts it on the beamline for you. And as I've already shown you, we're already pretty good at being able to pick up a sample and putting it on a beamline to scan it. So although it seems like that's a very kind of far away goal that's somewhere in the distant future, a lot of the individual pieces do exist in some way, shape or form. It's putting these things together that's definitely going to be where the challenge is. So finally, to conclude, just to say, at the moment we do have capability for remote access at facilities. Obviously, we can remotely log into machines and run things manually, but we also have the ability to do kind of robotic mounting, removal of samples, put them in place. We can look at data as it's coming along, and this could be raw data or processed data. I've already demonstrated we can run algorithms against raw data. And we do have an access route for a truly analytically driven feedback loop. But the one thing that you do need to look out for, obviously, is depending on the time frame that your experiment is taking place in, you need your result to come back in a timely fashion so that you can do the next step. There's no point if you have to wait 15, 20 minutes for something to proceed when your scan takes a second, because you're just eating away at time. But I do see us being around about here at the moment, which is where our algorithmic development is ongoing. And we need to do more kind of validation and testing of this. And something that we definitely also need to keep an eye out on, this is part of remote access generally, but the idea of authentication, making sure that we don't give processes the ability to run amok and do whatever, but also checks and limits on scans to make sure you don't end up driving pieces of equipment into each other and whatever else. And with that, that is my entire presentation. So I think there is potential for some questions, or are we saving those for the end for the panel?
No. I think we're definitely open to questions at the moment. So I think the audience can put questions in, type them into the box, and also panel members, if any panel members have questions for Tim, just feel free to kind of make yourself known by switching on your cameras and your microphones and asking away. I'm certainly going to lead off. I'm going to take the opportunity and seize my my position at the top of the queue to ask you some questions. No, it was really interesting, Tim, a nice kind of breakdown where things can actually happen. And one thing I would say, I'm really quite interested in the kind of intelligent scanning thing at the moment, probably just because I was at a workshop on it last week and it's the last thing I've seen. But I'm just wondering what techniques or what experiments at Diamond do you think are kind of the closest to that kind of thing happening, or where do you think it's going to have the biggest impact at Diamond?
So this is why I put in my original title slide, when, where, and why, because I think in terms of intelligent scanning, in a lot of the areas that I work with, one thing that keeps coming up time and time again is this idea of beam damage. So I've irradiated my sample, I've gathered some data. If I compare it to the previous scan, or maybe I take the previous 5 scans, average those and compare it, is this scan significantly different? And if I'm not expecting there to be a difference, so if I'm looking to acquire a lot of data until I've damaged my sample, or if I want to just have a qualifier that there is a significant difference at this point, I think that is the first place where there may be some intelligence in scanning. So I've damaged the sample, stop it, run the next one, or flow something, or change some parameter such that I'm looking at a new part of the sample. I don't think necessarily, however, that that's something for machine learning. I think you can do that through statistical, more classical methods much more easily. But I think as a starting point, there's so much interest in so many different areas and looking at those kind of qualifiers that that's a very piece of low-hanging fruit that people would be interested in. Building on that, there's definitely scope for a lot of different dynamic measurements for endpoints. So I've got something I'm synthesizing. I know there's an endpoint. This is what I'm aiming towards for whatever reason. And then once you've got the ability to look at differences and work out where you have some place of interest, you could then look for key points of interest. So synthesizing some kind of particulate or colloidal dispersion in a liquid, putting a thin film on a surface when it gets to a certain thickness. We want to stop this experiment for whatever reason. I'm straining a sample. I'm looking for a particular qualifier for this is when it's about to break, maybe. And that is, I feel, where your machine learning, especially like quick inference, comes in, because you can quickly classify, have I got to a particular place? Have I got to a particular condition? You can probably do that a lot faster than you can with a lot of classical methods.
Thanks very much, Tim. And any further questions from the panel? If there's not, I do have another thing I want to ask you about, which is I want to specifically your Bayesian analysis stuff. So yep. This is really nice, and it's clearly the way people should be analyzing reflectivity experiments. To what extent is it the way that people do it, and if not, what are the barriers to people doing it, and how do you encourage them to do more of it?
So currently, the only people that I'm aware of that have gone down this route for analyzing reflectivity data is us. So it was one of these things that when Andrew and I, or I say Andrew and I, when Andrew really came to me with this idea, I thought this sounds very methodical, and this obviously will give you potentially quite a deep insight into what's going on, because you'll have some kind of statistical backing for what you're saying, rather than just I feel this is what we should be fitting. But the way that community currently looks at their data, there is a large amount of intuition based upon the system rather than looking at it from a more statistical standpoint. The ways to, I feel, get people to buy into this is basically by presenting this as a rigorous foundation for how you can go about looking at your data, and then providing the tools to get people into this in a more timely fashion. So obviously, if you have to reinvent the wheel every time, or if you have to start going back down to base level foundations of software writing, that presents itself as a barrier. And one of the things that we did do when we were conducting this work was to put a certain amount of this online, so that people can go and be able to reproduce the paper for a start, but also look at the packages we used, how we implemented them, and what's going on there as well, so that people can then implement these as well. We're in a slightly special position, I guess, at Diamond, because there are a number of data analysis scientists that are tied to certain techniques. So another way of being able to help people adopt it is to essentially offload some of their troubles onto somebody else and say, look, you know, we're going to look at this particular system. Do you have any ideas as to what would be good to fit? And you could say, well, you know, we've done this work previously. We could push in this direction, or, you know, we already have some of these results for very similar systems. Maybe you want to implement some of these kind of things as well. But obviously that doesn't necessarily scale, because not every facility has data analysis scientists working at every single beamline that can spend the time looking at every single visit. So when you're starting something out and piloting it, that can work quite well, but whether or not that's ready for full deployment, yeah, probably not. So, guessing
I think forcing a Bayesian course on undergraduate chemists wouldn't be a terrible idea.
It probably wouldn't be. I mean, I never had one as a chemist, as an undergraduate or as a PhD student, but I've got into it since. So there's definitely quite a lot of, I think there's quite a lot of statistics that are very important and underpin a lot of what happens, not only at facilities but also in the lab as well, that maybe don't get taught so rigorously absolutely everywhere. And maybe that's something for courses to look at. Maybe that's something more for the Royal Society of Chemistry, I guess, seeing as they do vaguely approve certain courses. But that's a slightly larger, different.
A bit beyond our remit for now. No, that was great. Thanks very much, Tim. And I know Alessandro's talk is pre-recorded, and I know it runs 2 minutes over, so we better move on quickly to that. But thank you again very much. So Sarah, do you have Alessandro's talk?
Yep, I'll switch over the presenter now and play the video.
Great.
I would like to thank you very much, the organizer, for inviting me here and giving the opportunity to present our latest advancements here at the Big Data Science Center at the Shanghai Synchrotron Radiation Facility. Today I would like to introduce the result of our efforts deploying the Big Data Science Center here at the Shanghai Synchrotron Radiation Facility, which resulted in the first super facility platform here in China and one of the few worldwide. The Big Data Science Center, I will call it from now on BDSC, and the Shanghai Synchrotron Radiation Facility, I'll call it SSRF. They are part of Chinese Academy of Science and Zhejiang Laboratory. First of all, a bit of geography. So we are located here in Shanghai, and if you zoom in this area, you will see that in Shanghai we are located here with SSRF, about 20 kilometers from the two airports in Shanghai. If you keep zooming here, you will end up with a top view of our SSRF campus, where you can see the synchrotron ring located here, and you can see this is the free electron laser part of our campus too. And here you can see the BDSC building. So we at the BDSC are covering the whole scientific computation of the entire SSRF with all its beamlines, which are at the moment 13 in operation and many more planned and to come. So we take care of the whole data science and scientific computation needs of the whole SSRF, allowing to increase the scientific productivity of our users. SSRF is a large national synchrotron facility, and as such is a place where multidisciplinary and multimodal science and technology are run on large scale. And we indeed are presented with a great challenge, which is the development of scientific computation platform which is able to handle multidisciplinary and multimodal science. Which is the top issue for us is not only an issue for SSRF. It's not only an issue for China. This is a worldwide issue, and it's called a big data deluge. The big data deluge means that since today, large facility like the synchrotron and many other like neutrons reactor and X-ray free electron laser are equipped with more and more advanced detectors. These detectors produce a huge amount of data. And you can see that we have estimated with the conclusion of the phase 2 here at SSRF that the SSRF will produce every year about 30 petabytes. And these are raw data. Then this will increase even more, including the processed data, up to 100 petabytes per year. This is a huge amount of data. There is no university, no department, no group worldwide which has enough human resource capable of analyzing all this data and capable of producing scientific meaningful result out of them, and therefore technological advancements. This is the major issue that we wanted to solve with our big data solution at BDSC. In fact, if we keep going like this in the near future, we won't be able to enable proper science anymore at a large facility, because the amount of data will be humongous to be processed, and there will be not human resource to do that. Therefore, we are pushing worldwide as an international effort to develop further the big data center at large scientific facilities, and therefore to forget a bit the data archive approach, because with the user would ever get archived for a long time and a large scale, unfortunately got forgotten. And this means that a lot of data nowadays worldwide are just wasted. Users come at our large facility, do their experiment, produce a whole set of data. Of this data has been estimated that worldwide 60% of them are analyzed, and 40% of them, unfortunately, of all the data produced from all the large facilities worldwide are wasted. And therefore, let's imagine how much science is hidden and lost in it. We at the BDSC want that the user process, analyze, and publish all their data. If we achieve this, then we'll obtain a dramatic increase in scientific discovery and technological advancements from our user at all the large national facilities worldwide. Therefore, what is our solution to that? I will show you our solution, and then I will present a bit of history, go a bit backward, showing how we reached this solution. Our solution to this problem has been the development of a big data framework deployed here at the BDSC at SSRF, which is engaged in the creation of machine-readable data pipelines targeted at enhancing and augmenting large scientific facility with AI and robotic automation. So as many of you know, nowadays there is a huge hype on artificial intelligence. But the real issue, the real question for me is, if the machine is unable to read the data, how the machine can learn from the data. That's why we at a large scientific facility face a huge challenge, because we here, as I say, we're multidisciplinary, we're multimodal, and we have not only beamlines, we have control system, we have user interacting with their experiments, with publication coming out from their experiment, with web portal interface interaction, analysis, application running. All these are unrelated data sources which are not readable directly by machine learning. So the first very objective of our big data center has been to create a big data backbone, as you can see here. The duty of this backbone is to tag all these unrelated sources and adapt them to transform them to unify universal big data uniform formatting system, and create therefore a uniform format out of them that is readable by machine. If this is done, then what we have achieved is a big data framework supporting machine readable and AI ready data format. Then now we can train our artificial intelligence through machine learning. Even further, with our future endeavors, which are now planned, we are planning to connect our BDSC back with a control system at the beamlines, so the artificial intelligence can learn from our big data framework whatever is happening in terms of experiments at SSRF from our users, and then adapt the experiment and automatically send the feedback to the robotic automation at beamlines. This means that we have achieved like that real-time experiment optimization through artificial intelligence and big data technologies. How we've done that at the BDSC at SSRF, first of all, we started when the BDSC was just established. We have a lot of disordered data. So the first things we did is to centralize and order and tag all the data set here from all the data source at SSRF. This is the necessary basis for AI at SSRF. Once achieved, this is going to increase the number of scientific publications produced at SSRF dramatically through big data science, AI, and robotic automation. And in turn, this means that the user can then bring home scientific publication-ready results and not simply raw data where they have totally abandoned it at their own institution to analyze this huge amount of raw data. Our objective is to bring them closer to the final result they can publish on the journal of their preference, and this result should be produced as much as possible in real time. We help like that the user to increase their scientific publication, to increase their scientific productivity, accelerate the user scientific discoveries and technological advancements. How we did that? We implement a super facility. The super facility concept is actually a virtual facility. You can see at our BDSC, we are very much focused on user science. For us, it's important that the user are focused on their science, not on data science. So this is our major objective here, enabling user science to the most. In order to do that, we implement the super facility here. So this means the user come to the SSRF, run their experiment, and this will produce big data. These are then analyzed and studied to theory, algorithm modeling, but this must run somewhere and run on HPC cluster, which are at our BDSC. And not only that, we've also developed an interface to elastically scale out this workload to the Shanghai Supercomputer Center and to all the other national supercomputers here in China. All of that is connected with big data network. We use at the moment China Science Technology Network, but all of this that you see here is a backhand and is not usable by the user. So the only way to allow the user to use this advanced technology for science is through the development of software platform, as we have done. The software platform we provide to the user is the front end, and it can actually leverage all these aspects of the super facility in backend through the software platform. So when you interact with the software platform, only in that case then using the full big data potential, then it can achieve real-time data interpretation and therefore increase the number of the user publication. How we did that? We automatize the entire facility data life cycle from proposal to final publication. We actually use a metadata catalog, which we have inherited by the Scikit. So the Scikit then was reprogrammed and adapted in order to run on the whole large-scale facility from the beginning to the end in operation, full operations. So we collect metadata from all these steps here, from proposal, from sending the proposal, for the review process of the proposal, from the schedule of the bin times, from the actual bin time and experiment, and from the data analysis and interpretation process, and then from the final publication. Now, all of that then, once it's transformed in metadata, can be fed to the artificial intelligence through machine learning and neural networks. And this has been all packaged in a platform which we have here developed and called Artificial Intelligence SSRF Super Facility Platform, AISSSRFSP, which is a next generation big data scientific platform which integrates all the AI big data infrastructure for a large facility all in one place. And that is quite an achievement that actually we were able now to develop here and now to offer to our users. Of course, our focus is always on the bin time itself and the data analysis interpretation, because it's here where science becomes technology, and it's here where data science becomes science. And it's here we can really increase the scientific outcome of our users. Moreover, we are promoting a national scientific ID, as it is very important that our platform actually is provided with a unique ID, and this ID is the same the user use not only our synchrotron, not only to all the other synchrotrons in China, but also to all the other large facilities, neutron reactor, X-ray free electron laser, just one ID, and for all the other large facilities. This is fundamental in order to allow multimodal analysis. So we will have one ID and for our platform, and we are offering our platform as a national model where all the other large facilities can make use of it in order to allow for a unique national ID and for access to multimodal capabilities. So I have divided the AISSSRFSP large-scale project in 3 subcategories. So the first, very core and more important, is the big data framework, and the SSRF big data framework, which then on top of it we place a unified user interface and management system. And this is the interface that the user used in order to interact with our backend. And why it is very important, because actually the user don't know how to use the BDSC resource properly. So our then interface help them to transparently use HPC, so high performance computing, and artificial intelligence, AI, to accelerate their science at the beamlines. And when this thing is done, this means that we can actually then fit to artificial intelligence all the user experience, and then run automation, full automation at our beamlines. Now, the AISSRFSP is being programmed in a way to be general, so that actually we can plug in synchrotron, neutron reactor, X-ray free electron laser in just one single platform. That's why it's very important that we have a national ID here deployed. And we are planning to deploy also many machine learning methods, since our facility is a multidisciplinary one, so will require different kind of approaches. Once we envelope like an umbrella with a single platform all the facility here in China, we can really achieve large-scale multimodal capability. That's the objective of BDSC developing the AISSRFSP. So it's a vision which involves both the SSRF and also all the other large facility nationwide here in China. How we train our AISSRFSP, actually we divide the database in 2 parts, the metadata database and the raw data database. So with the let's see what is going in the metadata and what's going to the raw data. So the national scientific ID, it's of course feeding our metadata, but also the proposal ID, the experimental topic, the experimental requirement, the list of sample with codes, all is going inside the metadata. Meanwhile, feeding through machine learning the AI. Also, the user come to our synchrotron and do experiments. So the experiments produce big data, which then are moved to our raw database. But they also use a lot of parameters for their application, for simulation, modeling, and analysis, and this goes on the metadata. Meanwhile, the beamline scientists use a lot of parameters for beamline configuration, alignment, calibration. All of that are also fed to our metadata system. And then everything is moved to our BDSC clusters for processing and analysis, and scale out to the national supercomputers, and then are displayed back after processing. All the results are displayed back to our user through thin client terminals in as much as possible real-time user-friendly interfaces. All of that is then enveloped in a universal format, and in order to provide, which we use JSON, in order to provide a convergence of all the metadata, and therefore a better training for artificial intelligence. You can see this is not just a project, this is a real project run, real operations here at the SSRF. So you can see here our MX crystallography beamline totally automatized with robotics. And what's happened is during the experiment, our BDSC collect all the information, particularly focused on the raw data produced by the detector, and then the raw data, of course, then are analyzed by our BDSC, and then finally the user is presented with the final 3D structure of their sample. which are the final results they can use for their publication. Now, why it's important, why we are pushing so much to connect all the data from the beginning to the end in our big data framework, because once we've done it and train off artificial intelligence, then the artificial intelligence can feed back to the beamlines and adjust in real time automatically the beamlines in case the final results are not good, in order to reset the whole experiment with a new configuration which will produce nice result for our users to be as much as possible immediately published. So the past was that the user find their experiments were wrongly configured only at home after the beam times. What we are providing now to our user is the possibility of big data analysis, which reconfigure user experiments directly in real time during the beam time. So the user therefore will no longer bring home bad data, but only good results. On top of this, we are providing the user with a universal interface, which acts like a front end to the big data framework backend, as we said before. This universal portal will enable the user to actually interact with the BDSC in many ways and with many interactions. And also it will allow the user transparently to use our big data platform enhanced with AI and HPC capability. The user can log in from our universal interface, and then it will be presented with a personal page where through big data visualization, the user can actually see in one single page all the data collected from all the user experiments at the SSRF. And furthermore, they are all linked with all sorts of other information. They will be linked with proposals, dataset, experiment, achievement. And also the user is presented with a beam time calendar where actually the user can see all his beam times. And also it's presented with a job scheduler where he can use in order to submit analysis task from his data to our HPC nodes. One of the most important features of our platform is giving the possibility of one single platform for the user to select his data that he produced during an experiment at SSRF, select the cluster where he wants to run, so BDSC or the supercomputer, national supercomputer here in Shanghai and in China in general, and then select the application to analyze this data, and then in one single interface, the application will run in real time on the user data using HPC nodes. All of this will be provided user-friendly and never leaving the interface that we are providing. This will dramatically increase this user scientific productivity here at SSRF. After BDSC was in fact deployed at SSRF, we achieved real-time results here. On average, results from large-scale beamline experiment are delivered in 10 minutes. The BDSC is now fully operative 24/7 with the user, and the BDSC dramatically accelerated user scientific productivity at SSRF, increasing it by a factor 5. All of this resulted in an invited paper for the focus collection on machine learning for large-scale facilities on the Machine Learning Science and Technology journal IOP Publishing, which has been accepted and now in press. Our platform does not run only on one single beamline. It runs on multiple beamlines here at SSRF, and here you can see a list of all the beamlines the platform is already operative on with the users. And as with the users, also with the beamline scientist, we provide the possibility to make full use of the most advanced big data, AI, and HPC technologies for science. In fact, the beamline scientists do not know how to build experimental data pipelines to enhance their beamlines with a BDSC capability. We at the BDSC are in charge, in fact, also of building these pipelines for them. Further advancing the scientific capability at SSRF with the most advanced technologies. The AISSSRFSP has been now proposed by the BDSC as a national platform for China, as we've achieved a state-of-art user experience and increased SSRF scientific performances, therefore realizing an algorithm cloud to solve scientific problems and interface them with national supercomputer facilities. If we are able to promote our platform as a national model, in fact, we will realize a national distributed platform. And this platform will provide one single interface for all the national facility in China. Therefore, the user will be capable of multidisciplinary and multimodal science through the use of one single platform, accelerating dramatically its scientific capability as well as the capability to produce technology out of science. Thank you very much for your attention.
Great. So obviously we can't ask any questions of Alessandro at the moment, but do feel free to type anything in if you have them. I'm sure they can be passed on, and maybe you can get in contact with them via WeChat or something like that. So next up, we have Stuart Campbell from Brookhaven, who is going to tell us about the work that they've been doing there on the latest upgrades.
My slides working okay? Yes.
Looks good. Yeah.
Awesome. Sorry. So thank you, everyone, and thank you to the organisers for the opportunity to talk about the work we're doing at the NSLS2. My name's Stuart Campbell. I'm from the National Synchrotron Light Source 2, which is at Brookhaven National Lab. So to start with, I just want to say a big thank you to all the people at Brookhaven and other light sources and other institutions and projects that we're working with that underpins a lot of the work that's presented today. Unfortunately, there's not enough space to include them all by name. And I'm just going to do a very high sort of level summary of the work we've described in the two papers that are in this special edition. And my collaborators on these papers are here. Particularly, I'd like to thank Dan Olds, who let me steal some of these slides for this talk. And these people are generally a mix of computational scientists, accelerator scientists, and beamline scientists. So we have people from all areas of the NSLS2. So the NSLS2 is it's a 3 GeV synchrotron. It offers a very coherent, intense synchrotron light beam that ranges from infrared to hard X-rays. So we are the newest synchrotron light source in the DOE complex. So we basically sit in that nice Goldilocks area between the ALS, which is a soft X-ray source, and the APS, which is a higher energy hard rate X-ray source. We've been online for just over 5 years, and at the moment we're running about 30 beamlines, and the ultimate capacity is about 60. So one of the underpinning technologies that we're using to leverage a lot of the AIML work that we're doing is we have a very similar to, like Tim mentioned, for Diamond Light Source, we have a consistent data acquisition and data management platform across all the beamlines. It's called Blue Sky, and so this gives us a uniform way of collecting metadata across beamlines, both from user-defined metadata and also metadata that we collect automatically, and we try and collect as much as we can up front, because obviously users will not always go back and label data afterwards. So this gives us a very sort of rich data set to start to use for things like training sets for data. And so one thing we've done is we focused on standardizing the APIs to these data sources and become a bit agnostic to the actual backend file formats. So the API to search for, the title is the same as it would be for the detector data, and all the data structures are fed back as basically Python data objects. And also then we use this same infrastructure for storing any AIML training or decisions that are made as we're using the algorithms. So what sort of things can we use artificial intelligence for at a facility like NSLS2? So the main areas that we're working on at the moment are fault detection, alignment, ensuring data fidelity, efficient data collection, and then processing and analysis. And this all while trying to keep stable operating conditions and making them easy for the non-expert to make use of. So the NSLS2 and accelerators are a very complex machine, and even though the NSLS2 runs with a high level of reliability, sometimes things do break. And when they break, they generally require a wide range of talents from domain scientists, engineers, software developers, technicians to try and diagnose and fix these breakdowns. So this, as you know, a beam time is very precious. Our beamlines are all oversubscribed. So if you start, if you lose some beam time, it's not always possible to reschedule that. We do at the moment, we employ various thresholding alarms and rely on the staff's intuition to make when things break. So, for example, in the blue sky system, if like the beam trips or something, we do pause the scans. But, unfortunately, if you're doing a time dependent study, then, the physics or chemistry of the sample won't stop just because you want it to stop. So one area we're looking at and trying to work on is trying to do what we call like a weather forecast for the stability of the facility or the beamline and the accelerator. So one thing we do have is we have over 100,000 variables that are monitored at the individual frequencies, and so this we have this since ever the NSLS2 started. So we have, I think it's roughly 50 terabytes of data gets produced a year for this archive, and then also obviously we know when we've had fault conditions, and this then is in another database, and for example, the fault database I think is about 1 megabyte, so you can see it's a very small data set within the larger data set, but this provides us a very good training set for supervised learning. So then we can try and do some anomaly detection to try and head off faults before they occur, or reduce the downtime with rapid diagnostics when they do occur. But one thing we want to do is that, to provide a sort of a stability weather forecast to the users. So if the users are wanting to perform a very time critical dependent study, and the forecast is that the machine may not be as stable as it could be at the moment, then maybe they don't want to be running that scan at this point. Moving on to aligning the beamline, I don't think any facility really has a good global optimization of all the optical components of a beamline to get peak performance. We generally align only a small number of variables that hopefully are independent. And then, of course, as the electron beam profile changes, that you need to then redo this again. And the current methods generally rely on the experts and the expert control of how to do this. And so one thing we're working on is we do have a number of beamline simulation tools, and then coupling this with our Blue Sky acquisition system, we can simulate a mixture of motor motions and the source radiation. And so we've started to demonstrate this on the TES beamline at NSLS2, which is a tender X-ray spectroscopy beamline. And for this, there's two ways. The calculations are quite long. So we're looking to employ various interpolation methods to expand the training set with finer grid space. So then this will give us a good training set that we can use for supervised learning to, to be able to try and optimize the alignment of beamlines much quicker. So moving on to the actual experiments and how can we do them, better and more efficient. It's of course the best thing is all our users obviously plan their experiments very well, but of course life sometimes gets in the way and not everything always goes to plan. So there are things that you may have some something in your samples not behaving as you would expect, or some preliminary analysis leads you to think that you need to make a change of your plan of what you were going to do for the experiment that you originally proposed. So this can mean then decisions need to be made in the middle of the night. If you then also couple in things like high throughput experiments or mail-in experiments where you're mixing together lots of users data, users samples in the same in a sample changer. Basically this means that we have to rely on humans to be watching this, and of course we don't have humans that will be watching this 24/7. So we're moving and doing a lot of work in the areas of autonomous experimentation, and Tim mentioned some that we're working on. You know, we're involved with like Jamie Sethian and Marcus Nowak and Kevin Yeager on their autonomous experiments, and we've worked with them and we've developed a standardized interface into Blue Sky called Blue Sky Adaptive, that then you can plug in different agents, as you will, to perform different logic to guide the experiment. But to concentrate on this is the example that's in more detail in one of the papers in this edition. And so this was using reinforcement learning to sort of add a gamification to the beamline. So, you know, we give it plus points when it's in a good place in a region of interest on a sample, and negative when it's not. And that we can, pardon me, we can then improve the throughput and the efficiency of the data collection. And then we can also utilize autonomous, autonomous identification tools, such as the crystallographic companion agent, which is described with some work by Phil Maffetone, and there's the reference. So also the users, you know, we have a lot of users with a lot of different expertise. Some are first-time users, and they do not always have the expertise to quickly understand the data. And also it's very beneficial that they can, you know, begin the analysis and do some preliminary analysis while they're at the synchrotron, at the beamline, because it's much easier for them to, you know, if they realize they need to make an extra measurement, to do it while they're there rather than after they've left, and then they need to go through the proposal system and come back and do a set of experiments. So, you know, this is just an example of a simple clustering algorithm that, you know, highlights the different phases in a sample. You know, this is a sort of simple tool that, you know, it shows that, you know, these tools don't need to be fancy, they just need to be helpful, and anything we can do to help use the beam time more efficiently leads to be able to do more materials discovery in a more efficient manner. Of course, you know, the world has changed in the past year or so, and a lot of the work we were doing in remote access tools and mailing programs has ramped up in priority and have been accelerated. And so I think that a lot of the AI tools, you know, and the automation, the diagnostics, the assistance we can give to the users and the staff is now more critical than ever. And in my opinion, I think even when in the post-COVID era, a lot of these tools will aid discovery and operation of the facility. Even before COVID, we had seen the trend to more users not actually coming physically to the synchrotron. And so I think tools like this will just, you know, they will help in the way that we just do science in general. So to summarize, you know, our sort of high-level goals are that, you know, we're doing a lot of work in autonomous experiments, in a lot of different areas, and then being able to do prompt and automatic data analysis using, you know, this can range from everything to something very simple to something that requires a supercomputer. Improving operations from all the way from the source to the sample. So things like making sure that the, you know, fault detection, beam quality, and to make sure that, you know, we are measuring good quality data. And, you know, we do have a lot of underpinning technologies we've been working on. So a lot of the Blue Sky work we've been doing, which we work on now with most of the light sources in the US and some outside the US. And we have in there hooks for, you know, doing on-the-fly analysis, adaptive experimentation, and also then these all tie into a common data API that we can query any of these datas, and we can use this to, you know, generate training data sets. So I just want to do a plug that, you know, if anyone's interested in working with us or any interest, then please reach out. And that's it. Thank you.
Thank you very much, Stuart. That was great. So again, any questions from the audience, please feel free to type them into the box. And also from the panel, just feel free to flick on your camera and ask. So I'm again going to kick off. So I think I think you won the award for best title of the edition with the Gaming the Beamline title of the paper, which
I'd like to take credit for the name, but I think that was down to Dan Olds and Phil Maffetone.
Well, yeah. So congratulations to them on that. But yeah, I wanted to ask actually specifically about that piece of work. So when you're doing the reinforcement learning, was it altering the beam characteristics, or is it altering where it's scanning on some type of sample or something like that?
It's mainly in the sample alignment where it's scanning. So if you're on a weak scattering place or a stronger scattering, so that's the sort of, but that was really just the test we were doing, you know, and I think this could be used for a lot of different methods, but it was generally for the sample alignment and sample higher throughput. You know,
yeah. So amenable to scenarios where you have some kind of sample that you kind of raster around and scan.
Or you have multiple samples on a sample changer, and you can find where they are quickly. So
yeah, I can definitely see how that's interesting for a lot of these kind of high throughput experimental studies. No, really cool. I did also want to ask about. I mean, do you look at things like surrogate models for speeding up so you talked about simulations of beamlines that can take up to 10 minutes. Is there any looking at surrogate models or anything like that there?
So yes, there's a whole sort of area I didn't even talk about of, you know, using, because one of the problems obviously I think is getting good training data for some of the supervised learning model. You know, generally all our data is of low volume if you compare it to, you know, like images on Facebook, or, you know, we are orders of magnitude down on the volume of training data. So yes, we do, you know, whether they either be, you know, materials modeling or beamline modeling, we do a lot of, you know, just do lots of simulations with lots of parameters and then use those as a all different parts down the beamline. Sorry.
Yeah, so we've actually got a question in from the audience here. So from Joss Cooper, who many of us will know. So Joss is asking, at what point are you happy turning the beamline control over to AI versus users? So that is, what sort of risk analysis goes on?
I think at the moment, not sure. I think because it's a very sliding grey scale of you know, ultimately the sort of ideal would be, you know, we have an AI equivalent of the beamline scientist that can respond to problems at 3 a.m. in the morning and figure them out, but I feel we're a little way from that. So I think for like individual scans and things that are, you know, optimized, so things like the gamification things, that sort of thing is, you know, it's within, you know, there is no damage you can do. You're within the, you know, you're just scanning something. And I think a lot of the other things are, it really depends on the use case, to be honest. So a lot we already do, and I think a lot of the others are more to give the experimenter more information so they can make better decisions. So I think I don't think there's ever going to be a, you know, a golden time that will just say, right, we've got self-driving beamlines now forever. And so I think it's going to be a sliding scale between some parts and we already do, you know, hand over to an AI, but you know, whether you want an AI to do something quite radical in the middle of the night when nobody is there and some falters. I think these things, especially where there may be safety implications of what it might be doing, I think there's going to be a lot of testing and a lot of verification before that would completely happen. So
absolutely, and actually I think that this is definitely a point that we're going to take across the panel discussion as well. This is one of the things we're going to be interested in discussing. So just to give a plug to people to hang around for the panel discussion as well after this. So just quickly give an opportunity if anyone on the panel or anyone from the audience has any further questions from Stuart. For Stuart, please jump in. So I see Miguel has come online. Yeah.
Yeah, I have a question for you, Stuart. Great talk. I was interested in knowing which kind of tools you are developing for the new cameras, for the new users, as you said, that where the ideas come from. Is from user requests, or is the beamliner scientist who's telling you, well, I have quite a large number of new users which are blocked or have problems with this?
I would say it's a mixture, so, the team of people who've been working on, say, for example, they're a mixture of beamline scientists and I would say people who are more on the robotics side, and then people who are on the sort of data analysis, data science side. I think, yes, often it's driven by a spotted either, say, inefficiency we can see, or just things that I would say I don't know if there's any real sort of user request saying we need AI/ML for this problem. It's one of those sort of tools that we're trying to use where we think it's best to employ it to make the facility more productive. So, sorry, that's not a very specific answer to your question. But
did you already get some feedback, or this is something that is starting? Some feedback from the users saying, okay, this is really helpful.
Yeah, I think for some of the things that we employ, I think the users don't even know that they're using an AI/ML thing. They just see that their scans go quicker, or something goes quicker, or they're warned about something before they realized it. So that's the ideal, is to make the tools sort of accessible for the non-expert, but then give the accessibility for the expert to be able to tweak things more, which is what we've that's in a lot of the software we've tried to do for the controls and that for the beamlines, and that's what we've tried to do, and we're just expanding that into AI/ML as another one of those tools in the tool set to do things.
Thank you.
Thanks, Miguel, and thanks, Stuart. So, yeah, if no further questions, we're just about bang on time. So I think this is a good time to switch across to the panel discussion. So if I could ask the panelists to switch on your cameras and microphones, so we can all jump in when we need to. So first of all, I would also like to say to the speakers, if the speakers want to join into the panel discussion, please feel free to switch on your cameras and so on. You're more than welcome. But I'll just quickly introduce the panelists who haven't so far spoken. So we have Vincent Favre-Nicolin from ESRF. From ILL, we have Miguel Gonzalez and also Paula Muti. We have Jayan Thiagalingam from Rutherford Appleton Laboratory, who's head of scientific machine learning. And we have Kirsten Plees Van Dam from Brookhaven, who leads the computational science initiative there. So yeah, a really, really great panel, and looking forward to some interesting discussion on where we see the future of machine learning at these large scale facilities. So I think we've heard some nice talks about what people are doing at the moment, and also some nice ideas about what might happen in the future, but let's explore some of these things a little bit further. So I'm going to start with a relatively general question for all of you, and that's, what do you see as the biggest areas in facilities where machine learning can contribute over the next 5 years? So data collection, analysis, controls, which areas do you think are going to be the most important? So I see Kirsten already has a hand up. So yeah, please go ahead.
So I think in the near term, certainly on the data collection side, that there's quite a few research projects underway which are starting to translate into operation, which look at optimal experimental design, looking at what you should collect, what the next steps are, preparing the experiment, but then also guiding it during the experiment itself. I think pushing that further is definitely one big area where we see progress. There is at the same time an increase in activity, and Stuart talked a little bit about that, at looking at the operational side and what could be done there to help with an optimized operation. And then the idea is in the future to bring the two together. How do I optimize across facility operation and all the experiments that are going on, to see what we can do there.
Yeah, I think tying into somewhat the super facility that we saw some ideas from. So now Jayan and then Vincent will come to you.
Okay, and to add to Kirsten's point, I think so I see two different areas again. So one is definitely I see control as a major area to kind of upcome, partly because of the recent advances in reinforcement learning, particularly on the actor-critic methods. So effectively, what we have in the facilities is basically two-front. One is very mechanized version of robotics, effectively what Tim was discussing in his talk. Collect this, deposit there, do the next thing, and so on and so forth, without any form of intelligence on the data that is being collected. So what I really see in future is actually the combination of those two. So the reinforcement learning control combined with data collection. So effectively, the system would collect the data, would assess the situation, whether it is really a meaningful one. If not, would repeat the experiment on the scientist's behalf, instead of actually flagging the scientist to say, repeat the experiment. So I really see these two are basic combination of the thing. And also in terms of collecting the data, it's just not mere collection of the data. What I really see is the machine learning would go one step further in terms of collecting meaningful data. So collect the data, would automatically filter the noises, and would see whether it is really relevant to the problem that is being posted. So in other words, the machine learning algorithms will become more context specific, more context aware of knowing what is being collected, whether it is really necessary or repeated. So those are my points. Those are my 2 points, Keith.
That's great, thanks, Jay. So Vincent, you were next.
Well, I think in the near future, so I agree with what has been said on data collection. But when you look at data analysis, I think this is a field which will see the biggest growth. I mean, firstly, because we are having more and more big data problems with many spectrums, images, or volumes acquired, which need to be analyzed as much as possible in an unsupervised way. I mean, there's no other way. And the other reason is because there are already many tools which have been developed in the community for this type of analysis. It's not necessarily something which has been developed at large facilities, but which are available. And what we need to do now in facilities is propose relatively standard pipelines to exploit all those machine learning automated analysis. And a lot of this can also be based on supervised learning models, which I think are slightly more acceptable by the community than unsupervised one, because it's less of a black box and there's much more confidence. So yeah, I think data analysis, it's already happening, even outside the facilities, and that's the easiest things to implement.
Yeah. So I think Stuart was next, and then Paolo.
So I was going to say for the autonomous things we have running at the moment, they sort of have to have an analysis component for the physics aware part of them. So, like the work we're doing with Jamie Sethian, Marcus Nowak, and Kevin Yeager relies on some analysis code that Kevin wrote to be able to do that physics based. And, some of the tomography stuff we're doing obviously needs some sort of appreciation of what tomography is and what it's doing. And so I think we're already at that point that we can't separate out control and analysis. They sort of become interlinked in some places.
Yeah. So Paolo?
I just wanted to say that I agree with all the colleagues and also with what just Stuart said at the very last. I mean, it is clear that the field in which we can see the easiest way to adapt this technique is the control, because everyone wants to gain factors in terms of to save beam time. But as soon as you move out from the standard application and you want to go into a physics-aware machine learning, then it is very complicated to distinguish in between. And actually, we see clearly that if you give the wrong model to the machine, I mean, all the autonomous part it just screw up. So the two things are very much interlinked. But on the other hand, having a pure machine learning based analysis without the control part, I think that for these we have to gain the battle against the old school in which that believes that they can always do things much better than a computer. And this is a battle that we are not yet ready to win, I believe. That's my point of view.
I think there's quite a bit more work to be done on reproducibility of AI results and explainability to give people the confidence to use them in environments like this, where if something goes wrong, there can be real consequences.
I do think that people will be forced to use some of these, because if you look at the data rates of our facilities, they're becoming such ridiculous that you can't do the old way of analyzing by hand. But I agree with Paolo, it's going to be a struggle.
But this is not only a story which is related to the data rate, because if you take the neutron world, we don't have such a huge data rate. But where we really need help is and the other thing is that we do not have a tunable facility. We get what we get. And that's why we need to have other way to improve. And clearly machine learning is one of those, and it's relatively inexpensive.
Well, I was going to add, what just Paolo was saying, that of course, from the neutron point of view, the challenge about data quantity is not as big, but also to point that machine learning is not the solution for everything. I will say that the big challenge for us is that basically every year we run about several hundreds of independent experiments, quite often proposals with a very specific goal in mind, with already a clear way of analyzing the data. So the people coming to do the experiment, they know what they are doing, and it's not always clear that they can get any benefit. So really we need to focus in which kind of experiments can benefit. It will not be all of them. And then of course, the problem is, as well, Tim mentioned this, we don't have all data scientists on the facility. So in the end, a lot of this will be on the users. I mean, some users realizing that they can get most from the data using machine learning and then publishing this, and then most people will come. But I don't think that we can do everything. And in any case, I don't think that we should do everything, because it will not be really the solution for all our problems or all our experiments.
Mm-hmm. So I think Tim, you had one point, and we'll move on then after this.
So back when I kind of started looking at this reflectivity work that we published, so this kind of came about because we put out a proposal for PDRA, and a person called Andrew McCluskey started working on this particular work package. And one of the first things we did was go to a student-led conference which featured reflectivity quite heavily. What was interesting was we mentioned that basically the idea was to kind of automate reflectivity analysis using machine learning. And there were two very distinct camps that appeared in the room. There were the students who went, "This is amazing, it's going to analyze all my data, or at least help me out." And then all the PIs that went, "I don't trust it. No, not going to take that at all. No, it's not happening." Which is why the other paper that I showed or highlighted for neutron reflectivity, so this is the work that went on with Daniel and Joss, I feel has a kind of inroad or a kind of greater potential acceptance on the more kind of PI reviewer side of things to start with. So there is an inherent low level of trust in some of these things at the moment, because everyone's doing it and people feel it's got the high potential for garbage in, garbage out. But if all you're doing is seed parameters for a more kind of classically accepted fitting algorithm that goes away and fits the data and gives you either a first pass result or maybe the final result, but at least you can say, right, well, I did some inference, I got some parameters, I fitted that, and now I've got this data. You've got the students who are engaged with, "Oh my God, it's so much easier, isn't this wonderful?" And the PI's going, and I can also see that it's been, it's gone through a method and a kind of analytical route that I can get behind. And then with respect to time, as that becomes more normalized and you can see these algorithms are putting out seed parameters that are either incredibly close to or the same as what comes out of the fitting algorithm, you then have time to build up that trust so that people will then accept it. Or at least that's the kind of view that I had on it.
No, absolutely. And that leads actually quite nicely onto the next thing that I wanted to discuss, which is, what do people feel are the most critical steps for increasing user confidence and trust in the machine learning and AI approaches that we've been talking about? So, Vincent.
Yeah, I think in the end, I mean, you're always going to doubt, I mean, some artificial brain analyzing your data for you. But in the end, the trust, I think, should come from open data. I mean, if the data which has been used for a particular publication is available, then you can reproduce the results and improve them in the future. And that's not limited to machine learning techniques, but as we are delegating a lot of the interpretation to neural networks and machines, it's becoming more important. And this has to go also with open algorithms as well as open neural networks. If you can always reproduce the results, then there's no reason to doubt what was interpreted, because you can always go back. Anyone can go back, and that's very important. So this is why we are, I think a lot of facilities are moving towards open data. And I mean, at ESRF, I mean, the data of any experiment has to become public after 3 years after the experiment. And that's the one way to go.
Yeah, absolutely. And Kirsten, so I see you're popping in, Tony. We'll get to you next.
I think someone else had his hand up first. Was it you, Jayan?
Oh, sorry, Jayan. Sorry.
That's okay. Okay. So I think my take on this one is, I think before we go on to, sure, there are lots of things we can bring onto the table to kind of increase the confidence, like, you know, explainability and uncertainty quantification and everything. But I think before all that, I think my view is that we need to have a baseline against which we are trying to compare things. So particularly what happens when we really produce AI or ML solutions, now in the absence of any baseline, nothing is really good to the scientists, because they tend to kind of pretend that, okay, they're going to analyze one data set, they're going to do better than this machine learning technique. But what we fail to see is the whole throughput of it. So for example, the machine learning solution could really analyze thousands of data sets fairly quickly, but in the absence of any baseline against which you want to compare, so that becomes a serious issue, you know, whether it is good or bad. So that's where I would really start first, you know, have a well-defined baseline against which we could really compare. Thanks,
Yeah.
Absolutely, yeah. Kirsten.
Yeah, no, I completely agree with that point, and it's quite nice if you have what you often see is that people can't analyze all the data, certainly at the beamlines that have large data outputs, and so showing that with machine learning you can go through all of them and you get better statistics, you get a much broader distribution. That's always a good thing. But there is work to be done from the computer science side, because choosing the right algorithm to use for your problem is really important. There are methods that are just not robust. We've done studies on that, and you cannot reproduce the results. So reproducibility of results, that you take the same training data, you run this again, you run it maybe on a different system, and you still get the same answers, is an absolute minimum. Using different techniques on the same data and still be able to produce the same results is sort of the next step up. And this kind of robust method development is really important, to choose those and be very careful about that. I think that's a really big thing. If people see, you know, it's like a roulette, what you get out of your analysis, that's just not confidence building. And I think confidence can be lost very quickly if you have just a few results like that. People would say, okay, I'm not going to touch this, none of this works. So we have to be really careful what we put out there to the users.
Absolutely, yeah. So I don't know, Tony, if Jayan covered the point that you were going to make there, because Tony seems to have disappeared again. So I guess, yeah. Sorry, there, you're back now.
Okay, I'm back. Yeah, no, it was just that you know, the reproducibility and having open science, open data. The question is, I think actually the data produced by these facilities is a long way from being officially fair data, and I wondered what activities are being done.
So this is asking the facility, what are facilities doing to make their data fair?
Yeah, I'm involved in a small project at Diamond to look at that, but it hasn't made much progress yet. And I just wondered if there was an action to make data specifically fair, findable, accessible, interoperable, and reusable.
So perhaps people could, I see Vincent, you're...
Yes, making the data fair is extremely important. I mean, this all revolves about metadata, which is collected at the same time. You want to know the conditions, and you want to have a set of experimental parameters, which is minimum so that you can be interpreted. So that's extremely important. I mean, this is in our policy at ESRF. The data being fair is mandated. Of course, we need to convert a number of parameters or file formats so that it is as fair as possible. This is also why, I mean, a lot of facilities are using the nexus definitions for files so that we can include lots of parameters. And in the end, there may be also some parameters which are missing, which corresponds to the global conditions of the experiment. And this is why in the data which is made public, there is also the electronic logbook which is recorded during the experiment, and we hope that this will help. So it's not completely foolproof. I mean, there are always bits and pieces which could be missing, but at least I think that most of the data, most of the metadata, and the electronic logbook, it should go in the right direction.
Okay, I mean, I'm particularly interested. I agree the formats are important and so on, and there's quite a lot of standardization of formats, but it's the I in FAIR when the people who proposed the FAIR data principles talk about them being machine readable and therefore using things like JSON LD linked data protocols and having some sort of agreed vocabulary or even ontology is what's supposed to be needed in order to get some semantic information out. And I don't see much of that happening at the facilities.
Yeah, well, there are some fields where... Quite.
Sorry, Vincent, I was going to say that it's on the table, and in fact, both the ESRF and ALL, we are in a European project called PANOSU, Photon and Neutron Open Science Cloud, where the idea is to contribute and put all the data into the future European Open Science Cloud. Facilities such as Diamond, ISIS, and other national facilities are in an equivalent European project called SPANS. So it's on the table, and part of the project is to develop all the catalogs and all the tools to make the data accessible and being really able to use it by the users. So, well, this is starting, and hopefully it will give some fruits, and it will be available. So it's just to tell you that, yeah, we are aware of the problem and trying to do something about this.
No, I know about the European projects, yeah. My worry is that there may be some fair bigots who will insist you use semantic web technologies, and that's my concern, because I think those are too exotic for scientists to use by and large. Anyway, enough.
Stuart, I think you were...
So I'd say we're doing, a lot of the, I'll say, technical side of the developments to do things that you said, Tony, to enable them, the JSON stuff and everything, and not work. That was one reason we sort of tried to standardize on APIs for things rather than the actual format, because it gives you a lot more freedom to add things that aren't in the format. I would say the big thing at the moment that stands between us and FAIR is probably more political with our sponsors and our agreements with users and what we're allowed to make public. That's probably where our biggest bottleneck is at the moment. It's not the technology of doing it, it's the
but you don't have something like, for example, the Elixir project are using, not using semantic web technologies, but something related based on schema.org, which was the only thing that Microsoft and Google ever agreed on. And you can extend that with your own vocabulary. So they're using bio schemas, and there is some work at the RDA looking at science schemas, and I wondered if that was actually...
Yeah, so we are using schema.org schemas to look at, and we were just talking last week at how easy it would be to try and extend that for things that are useful to us, but
that would be good. I think that's a really interesting thing to do. Anyway, enough. I'm sorry.
So yeah, this can carry on at the FAIR data webinar, which is coming up sometime soon, no doubt. Oh, Tim, did you want to make a point there?
Yeah, just a quick thing. So, I mean, Tony, you and I both know that having metadata is important, but recently the thing that I found is that although the amount of willing to progress these things is always limited by how much resource and how much effort there is, if you look at the Lens and Leaps initiatives, which a number of us, I think pretty much everyone who's here actually has signed up to in some way, shape or form, there are commitments for these things that are like higher ups, exec board members have all said that these are important things we should do. So I've been using that recently as a way of kind of starting a conversation by saying, well, we've been told we need to do this, so maybe we should try and actually think about doing what we've been told we should be doing. But I also got another side message about the Expands project, because this is something there'll be a meeting later on this week on. But Diamond's actually leading on the ontologies kind of section in that. So maybe that's something that we could think about pursuing outside of this to talk about as well, I guess, at some point.
Yeah, it would be great to meet over coffee.
Someday.
It would be great to meet over coffee, but I might have to do it online.
And I saw, yeah,
divert the.
And Abigail McBurney is also written in from the audience to say about Expands and PanSoc, looking into fair data. So yeah, so that interesting stuff about data, but maybe looking a bit more at machine learning developments and so on as well. So what do people think are the most exciting developments in machine learning that could be applied in facilities? So we've kind of looked at the areas of facilities that could be used in developments in computer science and machine learning. What's most exciting there for you? JM, yeah.
Maybe I could rant a bit on this. A couple of things I thought I'd really mention. I'm sure that others will cover. So maybe for me, I think so one of the limiting factors for us to apply deep learning on facility data is basically lack of labels or lack of ground truth. So on that front, I think the recent advances in generative modeling is quite very important here. So what we can do on that particular front is actually we can take this even one step further. I think there are lots of initiatives that are already effectively simulating data sets that are really like real data sets, but yet simulated, but on the generative front. So what happens is when you're actually generating data, you can also generate simulated data sets in parallel. So that would be, that's one of the latest advances on the machine learning. The other one is very much on the reinforcement learning side of it again, particularly about the latest sort of advances on the actor-critic methods, very specifically on the policy gradient techniques. So those are very useful in terms of what Stuart was talking about, doing the fine-grained control of the beamlines or any other control aspects of it without having any form of ground truth. So these two, I think, very important advances in machine learning, but I'm sure that there are others that add to this one.
Yeah, so I think Kirsten was next up to jump in on that.
Yeah, I would have listed the same ones as well. So that's great. I think the one I would add is causal analysis, in particular when we look at beamline optimization, things like that. If something pops up that doesn't seem right, can we go back and can we find out where it's coming from? Going a bit forward, which will require more research, what we really want to enable is the collaboration between the scientist and the AI and the facility, and that will require new ways of exchanging mental models, of capturing. We do this a little bit for single experiments at the moment, capturing the scientific goals of the scientist and use that for the optimal experimental design, and working more in that area. I think that there's quite a bit more to do. Maybe the hope is at some point that the AI can come up with suggestions that would be helpful to the scientist. And it's the challenge there, to be very clear, is not coming up with suggestions. That's the easy thing, but coming up with those that are actually helpful. So filtering this down is the challenge here.
Absolutely. So anyone else have any particular areas in machine learning that they think that haven't been covered? I think Kirsten and Jayan have done a very good job of summarizing a lot of the exciting developments. So I kind of wanted to, because we're getting towards the end now, and maybe do a little bit of kind of crystal ball gazing, and wanted to ask people, to what extent do they think that we're going to see this idea of a self-driving facility within, let's say within the next 5 years? How far do you think we'll get towards self-driving facilities? So it's one for people to ponder a little bit, but if anybody wants to stick their neck out on that one.
But I would say that for us it's easy to answer, never. Because lucky enough, AI will never touch the reactor. So this type of facility. But of course, when we go to compact source, we can rediscuss. But I think from a more general perspective, I believe that the advance both on the facility driven by the AI, or let's say helped by the AI, and the conjunction with what we can do on the experiments on the beamlines, I think that this will happen more and more. I think that probably in the next 5 years we will have a large number of, let's say, the standard experiment, whatever this means, that are mostly ML driven.
Yes, yeah, I agree with Paolo that we're not all are going to be, but for the ones that are the more measurement based, the sort of structural biology or mail-in powder diffraction, the sort of, I can imagine those definitely being more fully automated in the next 5 years.
Yeah, I think Stuart knows we've had discussion at Brookhaven. It's less the technology that will hinder us. It's educating and getting the workforce that can work with these tools. That will be much more of a challenge than anything else.
Yeah.
How can you pay them as much as Uber will pay them?
Yeah. Yeah, exactly.
That's a simple one. We can't.
Yeah. We have to wow them with our exciting science. The only way forward.
But it is getting things like TensorFlow and that to be as natural for a beamline or a scientist to use as NumPy is, or something like that, I think, or SciPy hybrids. I think that's one of the challenges, because a lot of the stuff we don't need new AIML methods. We just need to use the ones that exist for a lot of the problems. Not all, but a lot.
So
absolutely.
You'd all be very skeptical. I've been people trying to persuade me to join something called the Nobel Turing Challenge, which is actually to develop an AI system that could win the Nobel Prize by itself by 2050. I find this a rather difficult vision to accept, but I suspect that listening to you, you're rather skeptical as well.
But who knows, if we get truly causal machine learning, perhaps we can do kind of hypothesis generation and we have it explainable so that we understand what it's done. Then maybe we get towards something that that looks a little bit like a Nobel Prize winner.
I'm still struggling with the Judea Pearl's Book of Why, which is his elementary account of causal reasoning. I'm working on it, but I haven't quite got.
So just very quickly before we wrap up, there were a couple of questions from the audience, which were, well, so one of them, I guess this is one that can go out to everyone at the facilities. If a researcher wants to study AI and machine learning for improving synchrotron stroke beamline operations, can they apply for funding directly to large facilities, or do they have to go through government or national bodies? So I don't know if anyone's got any secret funds that they want to announce that people can apply for, or I'm guessing the idea would be you should maybe talk to people who work at the beamlines and see, and perhaps you can work with them if there are ideas for doing this kind of thing.
I think the only thing I could possibly say on this front is similar to going to maybe a member of Beamline staff and saying, oh, I've got a really cool idea for developing a new scanning technique, or there's some really cool science, maybe we should apply for some funding to whoever, or do you know of anyone that could fund this kind of work, it would be a very similar kind of application route. I don't have a sofa in Diamond House, but if I did, I'm sure if I looked down the back of it, I'd probably just find lint and maybe a penny or two. So it'd definitely be that kind of route.
I think it depends on the scale as well. You know, if it's the scale of like joint PhD students and that, maybe, but bigger things, yeah, that we do have a few, you know, projects with DOE that are to develop these things, and so generally we don't have our own internal funds to develop a lot of the more research applications.
Vincent?
Yeah, we don't have any secret funds available, but there are definitely going to be some opportunities. I mean, at ESRF, we are beginning to increase our workforce on machine learning, so there will certainly be a few positions available near the end of the year. And there will be also some PhD openings specifically involving machine learning. So if you have a good idea, there's always a possibility to come work at the facilities. I mean, there will be positions opening everywhere. And if you already have a position, I mean, coming as a visiting scientist is always possible. I mean, it's a big field. I think all facilities are interested in this. So don't hesitate to contact us.
Yeah, absolutely. So, and I think keep your eye out for the next kind of set of workshops and so on that people are going to organize with facilities and machine learning. I'm sure there's so much interesting stuff going on in this area that there's going to be a lot of interesting things and people around to talk to. So I think that brings us very nicely to the end, but I'd just really like to thank all the panelists and the speakers today for what was a very enjoyable experience for me, certainly despite my having to multitask more than I'm strictly comfortable with. But thank you all very much, and hope to see you all again soon.
Thank you.
Bye.
Bye.
Thank you. Thank you. Bye bye.
Cheers. Thanks.
Bye.
I can't tell if how many people are. There we go. We've got a few people left. So oh no, that's good. Thanks, Jane. Thank you.
No
Thank
worries.
you
It's a pleasure. So we had a very good. Yeah.